All right, class. So now we're going to continue our discussions of acid and bases by discussing the differences between what we refer to as strong acids and strong bases versus weak acids and weak bases, okay? So how do these differ? How do strong acids and bases differ from weak acids and bases? Okay, in a very general way, we know that strong acids dissociate completely in water, and weak acids do not. But even with this, there is still a wide range of strength between strong and weak acids. There's a very wide spectrum, okay? The strength of an acid or a base is helpful to predict how reactions will progress, okay? We will learn to do quantitative strength analysis using what is called the pKa value to compare the different strengths of acids, okay? We will also learn to do a qualitative strength analysis. This is comparing the general stability of different structures, okay? So the first way that we will discuss is the quantitative method for determining an acid's strength. This uses numerical data to compare how strong acids are, okay? The Ka is the acid dissociation constant of an acid when it is dissolved in water. It is the measurement of an acid's strength or how much is dissociated when water is the base. Okay, now remember, we said in the last set of slides, an acid cannot lose their proton unless a lone pair from a base comes and takes it. Okay, we need to have a base to take the proton. Okay, in determining a Ka and pKa values, we will see that water is going to act as our base. Okay, so you can see here we have our chemical reaction, and we can see that Ha is acting as our acid or proton donor, and water is acting as our proton acceptor or base. And this is a reversible reaction. And we know that reversible reactions will eventually reach something called equilibrium. Okay, as a reminder, remember, equilibrium is when the rate of the forward reaction is equal to the rate of the back reaction. Or, to put it another way, when we see no change in the amount of products or reactants present in our reaction. Okay, the equilibrium constant is the concentration of products at equilibrium over the concentration of reactants at equilibrium. And for acids, we simplify this math by taking the concentration of water out of the mathematical equation. We call this value our Ka value for an acid. Each acid has its own Ka value determined by how much of it dissociates or loses its proton in water. If the acid is strong, will Ka be bigger than 1 or smaller than 1? Okay, hopefully you're all sitting there going, it will be bigger. If an acid is strong, that means it loses its proton very readily. It's ready for water to come and just take it away. That means we're going to have a lot of products, not a lot of reactants, so our equilibrium constant is going to be greater than 1. Okay, the inverse is true for a weak acid. A weak acid tends to hold onto its proton. It's not great at giving away its proton. So when water tries to come take it away, it's still hanging on to some of its proton. That means our products are going to be small and our reactants are going to be big, and our equilibrium constant would be less than 1 for a weak acid. Ka values are typically either very big or very small numbers. They can range from about 10 to the negative 50 to 10 to the power of 10. And so the size of these numbers are very hard to work with. That's a lot of decimal points, right? Now, if you take the negative log of the Ka value, that will focus you on only the exponent of the Ka value, which will now range from -10 to 50. And these numbers are much easier for us to work with. We call this value the pKa, and this is what we actually use to determine our acid strength. Okay, now again, remember, pKa is the negative log of Ka. We said that Ka can be anywhere from 10 to the -50 to 10 to the +10. That's a big range. So our pKa values, because we're taking the negative log, will range from -10 to +50. Okay. We also see that there is an inverse correlation between acid strength and pKa value. We just saw that acid strength means that we have a strong acid will give us a larger Ka value. But pKa is the negative log of Ka, and so the stronger the acid, the lower the pKa value would be. Okay, I've got this here in bright red writing because that's important to remember. Low pKa, strong acid. Okay, now here are some acids and their known pKa values. Now before, we said that a strong acid has a large Ka, and since pKa is the negative log of Ka, that means that we will have a smaller number as the pKa value. In fact, most of our strong acids actually have negative pKa values. Okay? Each pKa unit represents an order of magnitude of a power of 10. Okay, so what does that mean? So for example, H2SO4 has a pKa of -9. It is 100 times more acidic, or 100 times of a stronger acid than HCl, which has a pKa of -7, because each one of those units is a power of 10 since we're using a logarithmic scale. You can also use pKa values to compare the strength of bases, because the stronger an acid is, the weaker its conjugate base will be. This is a concept that we will come back to in much more detail when we discuss the qualitative way of determining acid strength. So when we know the pKa values of an acid-base reaction, when we have that information, we can predict which direction an acid-base equilibrium will favor. Okay, remember, higher pKa equals weaker acid. This reaction demonstrates a phenomenon that is always true in an acid-base reaction. Equilibrium favors the weaker acid and the weaker base. In this reaction, we can see that the right side of the equilibrium has the weaker acid because it has a higher pKa value. It has a pKa value of 18 as opposed to 15.7. That side is favored in the equilibrium, and we can see that by the way our arrows have been drawn. Some acid-base reactions are so favored on one side that they are essentially reversible. The pKa data can also be used to determine if this will be the case. Okay, so let's look at our reaction here. You can see that there is a very large difference in pKa values between our two acids. Okay, if we take the pKa value of the acid on the right and subtract the pKa value of the acid on the left, we can say that we have a difference of 34 between those two pK values. What this is telling you is that you will have 10 to the 34 more products formed than reactants. At that level, we say that the reaction is essentially irreversible. Okay, it's not in equilibrium because there is such a great difference between the two sides.